We'll now talk about how to solve the vanishing gradient problem using changes in the architecture of an RNN. In particular, we'll talk about LSTMs and GRUs. One question that we left behind was, how do you tackle the vanishing gradient problem in RNNs without changing the architecture? You could do a few things. You could use ReLU instead of tan H and sigmoid. Remember, ReLU does not vanish the gradient. It keeps the gradient, at least the positive, for the positive activations, it keeps the gradient as it is. You could regularize in some way. You could initialize the weights in some way that helps carry forward the gradients backward. And you could also consider using only short time sequences so that the gradient does not vanish within that short time frame. Let's revisit this problem of long-term dependencies. So if you had a situation where you were dealing with a sequence learning problem, which say wants to predict a sentence, the clouds are in the sky, or it wants to classify, say, the sentiment or the category of the sentence. An RNN may be good enough because the word sky may only depend on the word cloud, which is, say, just 2 words before, if you remove all the basic words in the phrase. However, if you have a more detailed sentence, a longer sentence, such as I grew up in France, I speak fluent French. Now, the word French at a particular time step may depend on some other word that was used several words ago. These long-term dependencies may not really get captured by an RNN because the presence of the word France may not really have an impact on the word French because the gradients may vanish between these two time steps. So we're going to talk about how we address this in this lecture. Just to recall, RNNs are trained using backpropagation through time. The limitations of backpropagation through time that we discussed were vanishing gradients and exploding gradients. Exploding gradients, we said we could handle using gradient clipping. How do you now address vanishing gradients using changes in RNN architecture? Are through LSTMs and GRUs as examples, and we'll discuss both of them in detail in this lecture. LSTM stands for long short-term memory. It was introduced way back in 1997 by Hochreiter and Schmidhuber, primarily intended to address this long-term dependency problem, although it was not in the same form that we'll discuss now, but we'll also discuss its evolution as we go forward. So here is the design of an LSTM. At each step t, in an RNN, we had a hidden state which the RNN block would output. Now, in an LSTM, we would have a hidden state which an LSTM block would output, and also an internal cell state which maintains the information across a temporal context. The cell stores long-term information, and the LSTM block can erase, write, and read information from that cell state based on whatever a context defines. The selection of what information you can forget or read or write is controlled by 3 gating mechanisms, one for erasing, one for writing, and one for reading. And on each time step, these gates could assume values: open, which would be 1, which would allow all the information to pass through; closed, which would be 0, which would not allow any information to pass through; or somewhere in between. You can also have an information lying between 0 and 1. These gate values are dynamic and are learnt and computed based on the input at a particular time step and the hidden state that comes from the previous time step. Let's see each of these components in more detail. A RNN has a general form of a chain of repeating modules. So if you took a vanilla RNN, the repeating module is perhaps a single layer with a tanh activation function. As we said earlier, it can also be not just a single layer but 2-3 layers, but that would be the repeating block that is applied to the input at each time step. So in this diagram here, you have an input xt minus 1 at t minus 1, xt at time t, and xt plus 1 at time t plus 1. And what you see here is a single neural network layer which has a tanh activation function, and the input at a particular time step xt as well as ht minus 1, which is the output of the previous RNN block, is provided as input. A tanh is applied, that gives us ht, and that ht is given as output as well as given to the next RNN block at the next time step. That's the vanilla RNN that we've seen so far, drawn in a different way. Let's now try to draw a parallel with LSTMs. LSTMs have a similar structure. Once again, it's a chain of repeating modules where you apply the same block at every time step. But now the structure of each block is not just one layer or 2 layers. It's different. It contains 4 different layers, and they are not sequential layers unlike the networks we've seen so far. They also interact with each other. We will see each of these layers in detail. So in this case, you can see that you have 4 different layers denoted by these 4 blocks, 4 yellow blocks. One of them is known as a forget gate, which decides to forget some cell content coming from the previous state. Another of them is known as an input gate, and that's why you see a sigmoid activation function here given by sigma. So these ones are sigmoid activation functions, and the reason we use sigmoid here is because we want the output to lie between 0 and 1. So the input gate along with a tanh activation function decides how much of the input should be written and also adds that new cell content at the end. So that's what happens here. And finally, there is an output gate which decides how much of the cell state should be exposed as the hidden state. So cell state is denoted as C sub t, and the hidden state is denoted as H sub t, and a part of the cell state is revealed as hidden state to the next time step as well as an output of the cell for further processing. Let's see each of these in more detail. So the cell state contains information which you can look at as a memory across a temporal context, and the information can flow across the cell state unchanged. If you see this diagram here, this is just the diagram from the previous slide with a few components grayed out for the sake of explanation. So you can see here that the information in a cell state CT passes as it is to the previous cell state CT minus 1. Why is this important? Try to connect this to the vanishing gradient, and we'll come back and talk about this point later in this lecture. The only thing that we have is a multiplication operation here and an addition operation here. The multiplication operation decides whether you want to forget something from a previous cell state CT minus 1 that contains a sigmoid neural network layer which has a dimension as the size of the cell state and has a value between 0 and 1 for each dimension of that cell state. So for each dimension of the cell state, you can decide how much of that information you want to retain using this multiplication operation here. This multiplication operation is a point-wise or element-wise multiplication operation. Then you also have an addition operation here which decides how much of that information gets added to how much of an information coming in gets added to this new cell state. Now let's talk about the forget gate to start with. The forget gate, which is one of the layers inside the LSTM block, takes input xt, takes input ht minus 1, very similar to the RNN block that we saw so far. Then it has a set of learnable weights, WF. Those WFs are learned while training. You have a bias BF corresponding to the weights, and then you apply a sigmoid activation function to ensure your outputs lie between 0 and 1. That's the output of the forget gate. And what does the forget gate do? It does an element-wise multiplication with the previous cell state Ct minus 1 to decide how much of that information should be erased and how much of that information should be kept. Similarly, the input gate decides what information to remove from the cell state. So the input gate also receives a copy of xt and ht minus 1 as input, similar to forget gate, has its own weights wi, a bias bi, and operates a sigmoid activation function to ensure the output lies between 0 and 1. And in this particular part of the architecture, you also have another component which takes the same input ht minus 1 xt. Remember, those are the only two inputs that you get to an RNN block. It's the same inputs here, which has its own weights wc, a bias bc, applies a tan h activation function so that you can have both negative and positive values, and you get an output c tilde t. Let's see how these are combined now. So the final cell state Ct is given by ft element-wise product Ct minus 1. So this tells you which dimensions of the previous cell state Ct minus 1 should be forgotten and to what extent. And the it input gate is multiplied with Ct tilde to decide what should be written on to the current cell state. So you have a cell state which is like a memory. In the current time step, you want to decide what aspect of the memory do you want to remove and what new content do you want to add to the memory. Finally, you have the output gate which controls what parts of the cell state are provided as the hidden state which goes to the next time step and the output. So OT is another gate similar to the forget gate and the input gate. Once again receives ht minus 1 and xt as input, has its own weights w0 and b0, sigmoid activation function because it's also a gating mechanism, and this is now combined with Ct, which is the current cell state, element wise, to decide what should be the ht that is provided to the next cell state, next state, as well as to the output. Now, to summarize these in equations, so ft is a forget gate which controls what is kept versus what is forgotten from the previous cell state. The input gate controls what parts of the new cell content are written to the cell. The output gate controls what part of the cell are output to the hidden state. All of them use a sigmoid activation function so that the output is similar to a gating mechanism and the values lie between 0 and 1. And Ct tilde is the new cell content that you want to write to the cell. So that's just a simple processing of the inputs. And Ct finally is obtained by forgetting some content from the previous state and writing some new cell content. Ft controls Ct minus 1 and the input gate it controls the CT tilde, which you ideally want to write onto the cell state. And finally, the hidden state is decides to read some content from the cell as output using the output gate. It again uses a tan H to maintain negative and positive values. Let's ask a couple of questions here to understand how this entire setup works. What can you tell about the cell state CT if the forget gate is set to 1 and the input gate is set to 0? Let's try to analyze this. The forget gate is set to all ones and the input gate is set to zeros. What would happen? From this equation here for CT, you can notice that the information of the cell coming in from the previous cell state will continue to be preserved because there would be no input that would be added due to the input gates being 0, and the C tilde would not have effect on the cell state. Let's ask another question. What would happen if you fix all input gate to all ones, forget gate to all zeros, and output gate to all ones? If you thought carefully, this will almost be the standard RNN. Think about it to ensure you can understand this. Why do we say almost standard RNN? The only difference now is there would be a tan H that gets added here, which was not there in the vanilla RNN. Now let's come back and ask this question. It seems like a complex architecture. One point to add to the discussion so far is that these 4 layers in an LSTM are not necessarily sequential the way we have seen networks so far. We of course saw skip connections where any layer could be connected to any other layer. Similarly, even in an LSTM, there are interactions between the layers to achieve a specific objective. Now let's try to ask, how does the LSTM really solve the vanishing gradient problem? The key to that lies in this highway here between CT and CT-1. We're going to call that the gradient highway. So whatever gradient of the error that you receive at CT will be passed on as is to CT-1. Earlier, we had to worry about that being mitigated by the activation function across a layer, so on and so forth. Here, if you notice, between CT-1 and CT, there is no layer per se. The only thing that exists between them is the output of the forget gate, which is just a vector. It's not a layer. There are no weights. It's just a vector. Why is this not a problem? This is not a problem because the job of the forget gate is to decide how much CT-1 should contribute to CT. So if the gradient is reduced to a previous state based on how much it contributed, that's a fair gradient. We won't be worried about it. The gradient does not get mitigated because of any other operations in the LSTM. It depends only on the forget gate, and the forget gate's job is to control how much of the previous cell state goes to the next cell state. So the gradient would only get mitigated by that much amount for each of the dimensions in the previous cell state. This allows LSTM to solve the vanishing gradient problem. So once again, if we go back to the equations here, this equation on CT tells us that CT, it depends on CT-1 only with respect to FT, while the second term here, the IT into CT tilde, could still be affected by the vanishing gradient problem. We don't worry about it because there's another component which will allow the gradient to pass through as is through the LSTM network to earlier time steps. This allows addressing the vanishing gradient problem in LSTMs. Over the years, since LSTMs came way back in 1997, there have been a few variants of LSTMs that have been developed. A couple of popular variants are One of them is known as an LSTM with peephole connections. The reason it's called an LSTM with peephole connections is in the computation of the forget gate, input gate and output gate, you notice that in addition to ht-1 and xt, you also provide ct-1 as inputs, and for the output gate, you also give ct as input. So you're allowing your gates to peep into the cell state and then decide which dimension you should cut down or which dimension you should let through. That's why these are known as LSTMs with peephole connections. Similarly, there has also been another variant known as an LSTM with coupled forget and input gates, where instead of having a separate forget gate and an input gate, the cell state is computed as ft element-wise product ct-1 and 1 minus ft element-wise product c tilde. So you had an IT in the vanilla version of the LSTM, but in this version, the ft doubles up to serve both these purposes. So ft tells you how much to forget and 1 minus ft tells you how much to let in. This is a variant that has been proposed. So the history of LSTMs, to summarize, is in 1997, Hochreiter and Schmidhuber first proposed LSTMs, and the learning at that time used was known as real-time recurrent learning with backpropagation. There was no forget gate in this version of the LSTM in the late 90s. Then in 1999, Schmidhuber again, their group introduced the forget gate into the LSTMs. In 2000, the variant with peephole connections was introduced, and in 2005, Alex Graves, who is probably responsible for the version of RNNs and LSTMs that we see today, introduced the vanilla LSTM as we know today with all the components. Over the last few years, especially between 2013 to 15, LSTMs started achieving state-of-the-art results on various applications such as handwriting recognition, speech recognition, machine translation, parsing, image captioning, so on and so forth, that they started becoming the default choice for doing sequence learning. However, while we won't have the opportunity to discuss this now, in 2020, as we speak, one of the hottest trends to handle sequence learning problems are known as transformers. Transformers use the idea of what is known as self-attention. In fact, in a recent competition, a summary report of all the methods that participated in that competition, WMT stands for machine translation. It's a machine translation, which is a sequence learning problem. When we say machine translation, we mean an application such as Google Translate to go from English to German or Hindi to English, so on and so forth. So with all the participants that provided entries to this competition, only 7 of them were RNN based, while 105 of them was transformer based. That should give you an idea of what is the latest trend at this time. In 2014, there was another variant similar to LSTM known as the gated recurrent unit, GRU, which was also proposed, which is also used popularly as an alternative for LSTM today. It was proposed by Chung et al. So the main idea here is very similar to the coupled forget and input gates. GRUs combine forget and input gates into a single update gate. It also merges the cell state and hidden state, and this is the overall architecture. Let's see this in some more detail. So in this GRU, you have only 2 gates instead of an input gate, a forget gate and an output gate. Now you have only 2 gates. These gates are called an update gate and a reset gate. So these look exactly the same as any other gates that we saw with an LSTM. But now the new hidden state content is given by the reset gate. The reset gate looks at ht-1, which is the hidden state coming from the previous time step, decides how much of that should be processed and then gives you an updated hidden state. So the reset gate selects useful parts of the previous hidden state and uses this to compute the new hidden state. And the final hidden state that's exposed out of the GRU block is 1 minus ZT. ZT is the update gate into HT minus 1 plus ZT into HT tilde. So the update gate controls what is kept from the previous hidden state and what is updated to the new hidden state. So to understand this further, let's ask this question: what happens if the reset gate is set to all ones and the update gate is set to all zeros? Let's try to analyze this. If the reset gate is set to all ones, this would just remain HT minus 1. There would be no impact there. It would just remain as HT minus 1. If the update gate is all zeros, the second term here would disappear because all those terms would become zeros. And the first term here would ensure you will have all ones, which means HT will simply become HT minus 1. And the second term, this entire computation from the current time step would not be considered at all. So effectively, very similar to what we talked about as one of the cases with LSTMs. Here, the same state from the previous time step would be retained and there would be no influence of the current input. To summarize the differences between GRUs and LSTMs, the input and forget gates of LSTMs are combined by an update gate in GRUs, and the reset gate is applied directly to the previous hidden state in GRUs. So GRUs have 2 gates and LSTM has 3 gates. What does this tell us? Lesser parameters to learn in GRUs. So learning could be better even with lesser data. GRUs don't have any internal memory, a cell state CT. Whatever is the internal cell state is also exposed as it is because there is no formal output gate to control how much of the cell state is output out of the cell state. In general, LSTM is a common preferred choice, especially if you know that your data has long-range dependencies or if you have large amounts of training data. But if you want better speed and fewer parameters and maybe smaller data sets, GRUs are a good choice to try for sequence learning problems. Your homework would be to continue to read chapter 10 of the deep learning book and these nice links on understanding LSTMs and GRU networks. And if you'd like to understand how LSTMs are trained using backpropagation through time, this is Alex Graves' book on RNN. Alex Graves, as we said, was responsible for designing the first LSTM. And there is also a nice code tutorial here if you'd like to understand the hands-on side. You would have assignments to also get a hands-on experience. But if you'd like to go through this, you can. Let's try to leave one question for you to take away. We did answer how LSTMs address vanishing gradients. How do GRUs address vanishing gradients? Try to look at its architecture and think about this question to ponder. References.